It's imperative when you're doing this stuff, your asymptotes are spot on, and that you do a good job with your graphs approaching that asymptote. The parent graph that we're going to look at is y equals 1 over x. That's our parent graph in this chapter. The rest of the stuff, not going to have parent graphs. So the second half of this section will not have parent graphs. Remember, your asymptotes need to be dotted and in a different color from the graph itself. Asymptotes are invisible lines. It's a value that your graph approaches but does not hit. We're going to spend a lot of time talking about the asymptotes today. I'm going to try to give you a couple of ways to determine asymptotes. If you can't figure out one of them, try the other one. The second method, you'll need a scientific calculator, a graphing calculator, or some sort of a calculator to figure it out. The parent graph y equals 1 over x. From the origin, the first thing you want to realize is that your y equals 0 and x equals 0 are your two asymptotes for this parent graph. They intersect at the origin, which means, excuse me, if you have a translation vector, the asymptotes move with the translation vector. From the origin, I only want you to plot 2 points. You can plot more, but you'll only need 2. Right 1, up 1, and left 1, down 1. For the parent graph, really, that's all you need. If you have stretching, you're probably going to want to throw in 2 more points just for fun. If you plug in a 1 for x, what's y? 1. Right 1, up 1. If you plug in a negative 1 for x, what's y? Negative 1. That's why we go left 1, down 1. In the parent graph, if I go right 2, I go up 1/2. Right 1, up 1/2. Oh, sorry, right 2, up 1/2. If I plug in a 3, it would be right 3, up 1 over 3, 1/3. If I plug in a 4 for x, right 4, up 1/4. Is anyone not seeing this? I'm going to tell you right now, if you duct tape your hands to the table today and you're not getting something and you don't ask questions, your end of chapter evaluation is not going to be pretty. You're setting yourself up. This is going to be confusing today. We're not going to get through everything. Ask your questions when you don't get something. Understand?
When you're saying you go right 1 and then up,
Plug in a 1 for x. What's y? Right 1, up 1. 1 comma 1. When I plug in a 2 for x, what's y? So we're going to go right 2, up 1/2. And right 3, up 1/3. So you can see how my graph, and I have those points plotted. Hard to see them. But you can see how the graph is going to get smaller and smaller and smaller, right? What are we going to approach? And what value for the function will we approach as x gets bigger and bigger? 1 over 3, 1 over 10, 1 over 100, you're going to approach 0. That's why we have this horizontal asymptote here. We do the same thing on the left. Left 1, down 1, left 2, down 1/2, left 3, down 1/3.
Isn't it technically like never touch the asymptote though?
Correct, that's what an asymptote is. That's why I said it's approaching 0. I didn't say it gets to 0. An asymptote is a value the graph approaches but never reaches. By the same token, we can't have x equals 0. Why not? Why can't x be 0? Why is there an asymptote there?
Because
Okay. Why can't it be 0?
Divide by 0 error.
Divide by 0 error, but that's just bad. You can't divide by 0. In your calculator, it says domain error or something. It gives you a little message that you did something that's no-no. Alright, so when x is 0, we can't have that happen. So as we get closer and closer to 0 for x, watch what happens. When x is 1/2, 1 divided by a half is 2. So we're here. When x is 1 over 10, 1 divided by 1 over 10 is 10. So at 1/10, you're all the way up here at 10. When x is 1 over 100, 1 over 1 over 100 is 100. So at 100th, you're way up there. And as you get closer and closer and closer, you're going to infinity. It's getting bigger and bigger. I only need 2 points for the parent graphs. Okay? This is how it works with a stretch factor that's vertical and a translation vector on that parent graph, y equals 1 over x. A is still our vertical stretch factor. C, comma D is still what we call the translation vector. Your domain is shun C, and your range is shun D. Shun, shun. You can also use the set builder notation, and you can say that your domain is all values of x such that x does not equal C. And y is all values of y such that y does not equal D. These are called exclusive domains. These are exclusive. All of our other domains have been inclusive. These are exclusive domains. So interval notation is here. Set builder is here. It's up to you.
Are we going to have any books on the stretch factors?
And I doubt it. This book does such a bad job of it. So I'm not even including it here.
What is the y equals a over x minus c plus d equation?
That's what we're trying to deal with. What happens if you get an equation that's not y equals 1 over x?
Oh.
Remember, we always start with a parent graph. Then here's the parent graph. Okay, let's say we multiplied this 1 over x by 3. What would you get?
Like 3 points.
No, I want to know if I want to take that expression 1 over x and multiply it by 3. What would you get?
3 over x.
3 over x. 3 over x. A is 3. If underneath you had x plus 4, and out here you had minus 5, then you'd have translations. Okay, it's no different than what we've been doing all semester, this whole, since January. Okay, A, B, C, D, and we don't really even have to worry about B, like Samana said.
So if we had an equation that was like 3 over x.
We're going to look at examples, so be patient. What I want you to know right now is the number on the top is your vertical stretch factor, and if it's negative here on the top, you have a flip. Right one up one becomes right one down something. Even if there's a negative in front of the fraction. Okay? C is whatever's the opposite of what's with x, plus or minus. And D is what's after the function.
What is this?
There isn't. See, there's just the number in front of the fraction would be up here. If you put a 3 here, you'd multiply 3 over 1, you get 3a over x minus c, right? Not going to happen. Occasionally you'll run into this. B plus a over x minus c. I don't like that. You guys will probably be able to work with it, but when I do that, my OCD kicks in. It's not supposed to be like that. The D is supposed to be over here, so I rewrite it. I can't help my affliction. You can probably overcome yours. Everybody good here? Look at an example. Okay. So here's the drill. This one's only got a stretch factor. So your list is going to be pretty short. You're going to have a parent graph, and you're going to have a vertical stretch factor. Technically, your translation vector, we know is going to be 0, 0. We want to know what's the horizontal asymptote equation, what's the vertical asymptote equation, what's your domain, what's your range. When you're dealing with parent graphs that are hyperbolas, your list is pretty long. But it's pretty easy too. Nothing's really changing. Your parent graph, y equals 1 over x. What's the vertical stretch factor? 4. We multiplied 1 over x by 4, we got 4 over x. There's no plussing and minusing at all, so the translation vector is 0. The horizontal asymptote, y equals 0, whatever the y coordinate in your translation vector is. Vertical asymptote, x equals 0, whatever the x coordinate in your translation vector is. And your domain is shun the 0 from the vertical asymptote, and your range is also shun 0 from the horizontal asymptote. So this one, there's nothing going on other than stretching. The origin stays right where it was, 0, 0. First thing you do, different color, horizontal, vertical asymptote for your translated origin, which in this case isn't translated at all, 0, 0, 0. Then we graph. The parent graph for 1 over x is right 1, up 1. What are we going to do? Right 1, up 4. The parent graph is left 1, down 1. We go left 1, down 4. Normally, that's all you would need. When I have a stretch factor, I usually do one more point right and one more point left of my translated origin. And since my vertical stretch factor is 4, I usually go right 4. In the parent graph, when you go right 4, in the parent graph, we go up 1/4. In the parent graph, right 4, up 1 over 4. We have a vertical stretch factor of 4, so right 4, up 1. And left 4, down 1. Right? That gives you a better idea how much slope, how much whoosh you have to your ramp. So from your asymptote, push the asymptote. And that was really lousy. From the asymptote, come down along the asymptote, hit your first point, hit your second point, and approach your asymptote. From the bottom, you come up. You come up along the asymptote. We try to come up along the asymptote. You can't seem to do it. Somebody had a question? Steven? Okay. Vertical stretch factor was 4. Go right 4 on your parent graph. Here's your parent graph. When you put in a 4 for x, how much do you go up? 1/4. What are we doing? We're multiplying the ups by 4. Right 4 up a quarter. We multiply a quarter by 4. And we end up going up 1. So right 4, up 1. No? Let's go back to the parent graph. In the parent graph, when x is 4, that's right 4 from the origin, right? I'm just picking a number. Let's start with 2. Yeah. Well, I did 4 because the vertical stretch factor is 4. And I know that right 4 is up a 4th. And when I multiply 1/4 by 4, I'm going to get a nice pretty integer 1. Okay? Now, you can do right 2, right 3, whatever you want. But I chose to do right 4. I did, because the vertical stretch factor was 4. Okay? So, when we look at this one, vertical stretch is 4. Right 4 up a quarter becomes right 4 up 1. Now, I answered hers. Did I get yours? You sure? Anybody not getting this? Try this one. Same idea. Okay, let's take a look. We make our list. We got a parent graph. We got a translation vector, a vertical stretch factor. We got a horizontal asymptote, a vertical asymptote, a domain, and a range. Parent graph is y equals 1 over x. Translation vector. We love that because there's no need to worry about moving. Vertical stretch factor, 3. Horizontal asymptote, vertical asymptote, domain, and range. So without translating, nothing really creative happens here. We're just making the graph taller by a factor of 3. First thing on my graph, asymptotes. Okay? So horizontal asymptote through the origin, vertical asymptote through the origin, dotted, different color. In a parent graph, right 1. In a parent graph, up 1. But in this graph, because we got a vertical stretch of 3. Okay? Thomas, what's my next point that I'm going to do over here? I'm not going to go left 1, down 1 now. What would you pick for right how many if you wanted a second point? Right 3 and times the 1/3 by 3, right 3, up 1. That gives you the right-hand side perfectly and gives you a really good idea of what the pitch of the ramp is going to be. Okay? Everybody with me so far? Robert, from the origin now?
Left 1, down 3.
Down 3, because we got a vertical stretch of 3, and it was left 1, down 1. And then the second point on that side, Hannah, you would go left how many? 3, down 1. And that would give you that graph right there. Does anybody see any issues with that? Look okay to everybody? Okay. Let's do one where we have to move it. Okay, let's take a look at y equals x minus 1 plus 2. And in this case, all we're looking at is a translation vector, no stretching, because on the top of this fraction is a 1. Parent graph is still going to be y equals 1 over x. Translation vector, be careful now. 1, not negative 1. 1 comma 2. Horizontal asymptote, therefore, is y equals 2. Vertical asymptote, x equals domain. We're going to shun the 1. Range, you're going to shun the 2. So first thing on my graph is what point? 1, 2. So I just make a little dot there because it's not really going to be part of my graph. And then through that origin that's translated, what do? Horizontal and vertical. 1, 2. No stretching here. Elise, where's the first point? From this intersection here? Right 1 up 1. And the next point?
Left 1, down 1.
Left 1, down 1. And then push your asymptotes. These are hyperbola. Those are hyperbolic functions that come in pairs. Every once in a while I get a couple of kids who only give me the right side or the left side of this. They don't put both hyperbola. You have to have them both. And again, your domain and range are exclusive, not inclusive. We say that we're just going to exclude the 1 for the x and the 2 for the y. Everybody good with that? Let's try one where you do both. Translate and stretch. Not only will you translate and stretch, but I can tell you that that negative 3 is going to cause you to flip it vertically. Give this one a try. See how far you can get. If you're stuck, okay, let's see if we can make the list and then we'll go to the graph. So starting with parent graph of y equals 1 over x. What is the translation vector? 1, comma 2. Not negative 1, 2. All right? Rachel, what's the vertical stretch factor? Negative 3. Taylor, the horizontal asymptote? And the vertical asymptote, Corbin?
X equals 1.
X equals 1. The domain for this one, Stephen. X does not equal 1, so we're going to shun the 1. In the range page, shun the 2, or y does not equal 2.
If it was inclusive, would it be like...
It can't be inclusive.
I mean, for any domain or range, would it be like the bracket is on it?
Yeah, well, that would be, you would never have inclusive of just a single number.
Oh, right, yeah.
You would have a greater than or equal to or less than or equal to be inclusive. Right? So, first thing we do is plot that 1, 2, and through that point, what happens next? Bless you. Asymptotes, vertical and horizontal. You don't even need to worry about the equations. Just go right through your translated origin. Natalie, first point. From the origin, right 1.
Down 3.
Down 3. Did you do another point on the right?
Yeah, I went right 3 down 1.
Right 3 down 1. The reason why we're choosing the right 3 is because in the parent graph you would go up a third, and when you multiply up 1/3 by negative 3, we go down 1. We get this nice, pretty integral point, and you get a nice, pretty hyperbolic graph on the right. Sumana, when I went left, 1. Up 3. Did you do another point?
Yeah, but I know I did it wrong.
Okay, so what should I do? Left 3, up 1. So when we come down here, we get a nice, pretty hyperbolic function like that. Don't stop after one hyperbola. Make sure you do them both. That's one of the common errors. It's not very frequent, but it's common that I'll only get this side, the right side or the left side. And I don't know if someone would get distracted by something else and then they forget to go back to it. I'm not sure, but hyperbolas come in pairs. Any questions on this one? Okay, these are parent graph y equals 1 over x. We're now going to look at ones that do not have parent graphs and are therefore not hyperbolic. They look hyperbolic, but they are not. We're going to come back to this in just 1 second. I want to go back to the parent graph that we started with, y equals 1 over x. Right? And I want to talk about where the asymptotes come from, just for a second. Y equals 1 over x. When we look at the horizontal asymptote, y equals 0, and the vertical asymptote, x equals 0, they're not random. They're asymptotes for a reason. Remember, an asymptote is something the graph approaches but never reaches. Why do we have a vertical asymptote of x equals 0, or a domain where we say x cannot be 0? Why is that true? But we don't know that there's a... So, chicken and egg. We don't know about asymptotes. Why can't, for y equals 1 over x, why can't x be 0? Because dividing by 0 is bad. And when you divide by 0, you get what we say mathematically is undefined. And when it's undefined, it's an excluded value. So when it's an excluded value, we have a vertical asymptote of x equals 0. That means any value of x that makes the denominator 0 out of bounds. And you'll get a vertical asymptote there. Now what about y equals 0? Why do we have y is equal to 0? It's the horizontal asymptote. This is a little bit more complicated.
Because 1 divided by nothing, or you can't divide 1 by anything to give you 0. So if y is 0, you can't divide 1 by anything to give you 0.
Right, but that's not necessarily why we go for an asymptote of y equals 0. I'm going to explain finding that horizontal asymptote in a couple of different ways. But I want to use this example right now to explain why this asymptote is y equals 0. And then we'll extrapolate that to where we're going with these rational functions, not a parent graph. All right? Good? All right. Some of you know that I suffer from migraine headaches. Some of you don't, but I do. I've always had them since I started teaching. And it actually, my very first one was when I was teaching a geometry class in the middle of the day. The lights, the power had gone out, and a lot of migraines are triggered with visual issues, and that triggered my very first migraine. And mine are pretty debilitating. Back before the medication they have now, it was 3 days for me. And the first 36 hours was dark room, no moving, brutal. So my migraines were a problem. And some like Paige knows I have these migraines. So she also knows my go-to snack is cookies. I can't eat candy because migraines like chocolate, not that I don't like a Three Musketeer bar or Reese's peanut butter cup, I just don't eat them because chocolate, nuts, those are all triggers for me. Cookies, obviously no chocolate chip and no nuts. Why would you put nuts in a cookie anyway? I don't understand that. But my go-to cookie is a sugar cookie. Yeah, they're all right. But my go-to, Snickerdoodles. Right? Love the Cookie Connection ones, the big honking Snickerdoodles. Love those. Costco would put them out once in a while, but I think Costco, they're like drug dealers. They put them out to you for a couple months and then boom, they're gone. That's just wrong. They should always be there. And they make a molasses cookie that's killer. Same thing, big. So Paige brought me a cookie one day, and I was so thankful. But I said, you know, this is a big cookie. We should share it. So we split the cookie, and she said, well, you know, everybody in the class isn't going to get any Snickerdoodle today. We should share with everybody. She's a giver. So we take the cookie and we break it up into 34 pieces. And every one of you gets a little piece of the Snickerdoodle cookie, which it's a big cookie, sure, you know, the Cookie Connection. So you would get enough so that you could put it in your mouth and say, geez, I wish I had a whole Snickerdoodle. All right? But then Paige would say, you know, there's a lot of people on campus today that aren't going to get Snickerdoodle. We should share with everyone. So we take the cookie and break it into 2,200 pieces of Snickerdoodle, okay? And we go out during second period and we say, look, we wanted to share our cookie with you. Here's your piece. Now, if you were lucky, you got a little piece of the cookie with a little bit of sugar and cinnamon on it, maybe, and you put it in your mouth and you go, yeah, there's something there. But yeah, you might have got that piece with just the white piece of flour that never got totally blended, and you put it in your, really? Nothing. Okay? But again, Paige, altruistic kid, she's a giver, and she's thinking, you know, there's so many people in the world today that don't get to have a Snickerdoodle. We should share with everybody. So we take the cookie and break it right down into the molecular level, probably, and we count out 7 billion pieces from this one cookie from the Cookie Connection. And we start going out to the world and saying, here you go, here's a piece for you, and here's a piece for you. And I think pretty much when you put that on your tongue, you know, I don't know what you do, like you lick your hand or whatever. I don't think you're going to take the Snickerdoodle cookie. And if your hands were dirty, you're probably going to be nasty. All right? In fact, you know what, Max? You can have my piece. Okay, so you get 2 of the 7 billion pieces. Maybe you'll be able to case it. You got 1 cookie. When you share it with everyone in the world, how much are you going to get? 1/7 billion. How much is that?
Nothing.
And yeah, let's just call it what it is. You're not even going to know. You're not going to be craving snickerdoodles because there was nothing to taste. So what I want you to understand is when there's 1 cookie divided amongst 1 billion people, you get nothing. Okay? Even if there was 100 cookies, you wouldn't get any. And anytime, number on the top, variable on the bottom, horizontal asymptote, y equals 0. It doesn't matter how many cookies there are. If you can count them, if you break them into an infinite number of pieces, the pieces are so small, you might as well say you got nothing. Your horizontal asymptote, number on the top, variable on the bottom, automatically y equals 0. Number on the top, variable on the bottom, y equals 0, always horizontal asymptote. How do you find the vertical asymptote? It's whatever makes the bottom equal 0. So just take the bottom, set it equal to 0. Don't make it complicated. It's that easy. So when we look at these rational functions, where you have a variable expression on the top and a variable expression on the bottom, the vertical asymptote's easy. Take the denominator, set it equal to 0, and solve for x. If you want to memorize this, have at it. But I would recommend against it, because you're not always going to have a linear expression on the bottom. Take the bottom, set it equal to 0, solve for x. That's your vertical asymptote. Later in the week, we'll come up with more than 1 vertical asymptote. Now, there's 2 ways to handle the top, the horizontal asymptote. One of them, the easy way as far as I'm concerned, you just cover up all the stuff. You put them in descending order and cover up everything but the first term on the top and the first term on the bottom. And then reduce. So we cover up, in this case, the b and the d, and when you reduce, the x's cross cancel, and you get a over c. Horizontal asymptote, y equals a over c. Vertical asymptotes are the easy ones. Set the bottom equal to 0 and solve. Horizontal asymptotes are more confusing, and this cover-up method here, where we just cover up all the terms beyond the first term, some people have a hard time with that. So here's an alternative method for you. If that's confusing, this will work. Plug in a 10,000 for x top and bottom, and then round to the nearest tenth. That'll give you your horizontal asymptote. So for our class, that'll be plenty close enough. Plug in a 10,000 wherever you see x, and round to the nearest tenth. So when we go back and look at these here, here's our generic rational function. And we look at this one, 3x minus 6 over x plus 2. What is the vertical asymptote? More specifically, x equals -2. Vertical asymptote, x equals -2. If you don't write an equation, that won't get you any points. A number will not help you here. The horizontal asymptote, y equals 2, I got 1/2, 3, do I hear anything bigger than 3? 3 going once, 3, do I hear 4? Anyone want a 4? Spencer, 4. No? Never mind. Cover up the plussing and minusing and reduce. 3x over x, what cross cancels? The x's, so you're left with y equals 3. If you don't like that method, 3 times 10,000 is 30,000 minus 6, 29,994, divided by 10,000 plus 2, 10,002. Round it to the nearest tenth, you're going to get 3. Okay? If really confusing you to cover up and reduce, plug in a 10,000 and reduce.
How do you get the vertical asymptote again?
What value of x makes the bottom equal 0? X plus 2 is the denominator, right? Can you tell me what value of x would make the bottom a 0? What's 0 plus 2? So it's not 0. Let's do it out. X plus 2 equals 0. How would you solve that?
Oh, negative.
How would you solve this equation right here? From
the 2.
From
From the 0.
Are you familiar with this phrase?
No.
Really? You've never heard of BS? You think I'm tricking you, right? Okay. Have you heard of BS?
Yes.
Do you know what it stands for?
Math.
BS does not stand for math. You think I'm messing with you here? If you've heard this phrase, BS.
What term does it mean in math?
Well, let's pretend we weren't talking about math. What do you think it means? Yeah, you don't want you know you're being set up, right? We're solving equations. When you do something to solve an equation, where do you need to do it? It starts with a B and an S. You subtract 2 like this. Yeah, both sides. And shame on you for that other thing. You can make it an equation and solve it, and sometimes you're going to have to, Jennifer, but can't you just look at that and see what would make this equal to 0?
Yeah.
Can you?
So it'd be negative 2.
What would I have to make x be to get a 0 on the bottom? It would be negative 2, right?
Yeah.
That's where this comes from. And like I said, later in the week I'm going to make it more complicated. But right now, just look at the bottom. What makes it equal to 0? What if I had x minus 5 in the bottom? What would x be that makes it 0? Positive 5. If I had 2x plus 3 equals 0, can you do that one in your head?
No.
So then you'd want to take something like that and say 2x plus 3 equals 0, subtract 3, divide by 2. Okay, and x would equal negative 3 over 2. X would equal 5 here. Are you seeing that? There's no problem with writing it down. If you can look at it and get it, great. If you can't, write it down and solve. Just like that.
Thank you.
Now you find the translation vector.
There is no translation vector. There is no translation vector. You can only have a translation vector if you have what? A parent graph. These do not have a parent graph. It's not an x squared. It's not an absolute x. It's not an x cubed, cube root, square root, log of x, natural log of x, exponential. It's none of those, right? It's not 1 over x.
Can I rephrase that?
All right?
Is that how you find the vertex?
There's no vertex here.
Well, for your graph is, right?
Ultimately, yes.
Yes, so 2, 3.
Time out. No translation vectors.
Okay. And I get
I know my asymptotes, right? Wrong. That's it. And then I'll tell you how I'm trying to get to where we're graphing. Your patience thing needs to be improved. Like a woman right now. Right. So again, let's talk about that graph. That graph right there is a lousy graph to do. That's why I just wanted to do the asymptotes. The graph is so far away from your asymptotes, you're off the graph. So it's not a very good example to start with. So horizontal asymptote is going to be y equals a over c when you're in this form. And vertical asymptote is x equals negative d over c. But seriously, that's only if you're in that perfect form. The bottom line is vertical asymptote. Set bottom equal to 0 and solve. cx plus d, whatever's in the bottom, it doesn't matter what it looks like. Just set it to 0 and solve for x. That's your vertical asymptote. Horizontal asymptote, descending order, top and bottom, cover up everything except the two first terms in the top and the bottom, and then reduce that expression. That'll be your horizontal asymptote. Every single time. If the cover-up thing is confusing, plug in a 10,000 for x and you'll be good to go. Okay? Plug in 10,000 for x, you'll be good to go. Just some reminders about asymptotes. They are limits. They are lines that the graph approaches but never reaches. And vertical asymptotes are always x equals, whereas horizontal asymptotes are always y equals. But they are the things that we're approaching. They're values of the function that you're approaching, both x and y, but you can never get to. Horizontal, vertical asymptotes. In this class, there's no slant asymptotes. In this class, there's only one horizontal asymptote, whereas there can be multiple vertical asymptotes. One horizontal, multiple verticals. Those are possible. Define vertical asymptotes. Set the bottom equal to 0 and solve for x. They are excluded values of your domain. Later in the week, you're going to find that you'll have to factor to find your asymptotes. The factor review has been updated. It's online in Chapter 1, very first file. So if you need a quick review because you're going to see all these factoring things again, go visit it. Okay? But these are going to be excluded values. Horizontal asymptotes are limits of what happens for the graph at infinity. Now that statement is factual, but in this course, it's not such a big deal. Okay, but in pre-calc, it's going to be a big deal to understand that it's not what happens in close when you're near 0. It's what happens when x goes to infinity. In this class, you can not cross an asymptote. We talked about this before. In this course, there is no crossing an asymptote with the graph. In other courses, you can cross an asymptote. Horizontal, you can't cross one. They have holes when you have a vertical asymptote. To get the horizontal asymptote, first term over first term, reduce. First term over first term, and reduce. Make sure you're in descending order. Okay? Any questions on the asymptotes before we look at how do we graph? We're almost losing Max here. Poor guy. Tough weekend or what? Really? What would you do? You'd think you'd be all rested for this class if that's the case, right? Over-rested. So let's look at this one. All right? Is there a parent graph for this function? That means there's no translation vector. There's no stretch factors. And if you treat it like that, which some of you may, oh yeah, the translation vector is going to be 1, 2, or 1, 1/2, or whatever, and the vertical stretch factor is 4, I assure you, your graph's going to be wrong. Now, I apologize in advance. I did apologize months ago for this. This is the only time, rational functions, that you have to make t-charts. And if you remember when we introduced the ABCD idea, I said, it works great as long as you have parent graphs, and it will work great in here except for rational functions. You have to teach it. Here's how it works. Vertical asymptote, x equals what? Horizontal asymptote, y equals 4. That's the first thing you put on your graph. X equals 1. Bam. Y equals 4. Bam. No, 1, 4 is not a translation vector. Can't be because we don't have a paired graph. The way that I want you to graph is I want you to make a T-chart. You can do as few as 2 points. You can do as few as 2 points, but no fewer than 2. How do you choose your points? Well, I want you to go to your vertical asymptote. I want you to follow the vertical asymptote until it hits the x-axis, wherever that is. Which is right here. Doesn't matter where it is. Then I want you to move from that vertical asymptote to the right on the x-axis until you hit the x value, the next x value that is an integer. So when we go from right here and we start moving to the right, what's the first integer to the right of the asymptote? 2. That goes into your T-chart. Go back to your asymptote where it hits the x-axis and move to the left until you get to an integer. What's the first integer to the left? 0. Now here's what you need to do. You need to plug in a 2 for x in the top and in the bottom. And whether or not you need to physically do it, y equals 4 times 2 minus 2 over 2 minus 1, and get 8 minus 2 over 1, which is 6. If you need to do it all out like that, fantastic. Do it. If you can plug in a 0 here and a 0 here and get, well, that'd be 0 minus 2 is negative 2 over 0 minus 1 is negative 1, and it would be 0, comma 2. If you can't do that in your head, you need to write it down like I showed you in red. Hannah.
Where'd you get the 2?
Okay, let's go to our vertical asymptote.
Yeah.
Follow it all the way down until we hit the x-axis. Move along the x-axis to the right until you hit an integer. What's the first integer to the right of your x-axis?
2.
2. What's the first integer to the left? 0. That's the 2 values you pick for your T-chart. You can pick others, but you have to be right and left of the asymptote. And if the further away you go from that vertical asymptote, the less idea of the picture you're going to have. Okay? Someone else have a question? So now we plot the point 2, comma 6. That point is going to go right here. It is the point 2, comma 6. 2, comma 6. 2, comma 6. You do not go to the intersection of the asymptotes and go right 2 up 6. That's not how you plot points. You're plotting the point 2, comma 6. Here's the origin. 2 on the x, 6 on the y is right here, this green point. From that point, push your asymptotes. And I'll be ecstatic with that. On the other point, 0, comma 2. Push your asymptotes. Put arrows on the ends, and I'll be really happy with the graph that looks like that. If you want to put in other values for x, be my guest. You can put in a 3 for x. Okay, you get 12 minus 2 is 10. 3 minus 1 is 2. 10 divided by 2 is 5. So you would get the point 1, 2, 3, 1, 2, 3, 4, 5 right here. But I don't need you to do that. Do it if you want to do it. Okay, the further away from your asymptote your first point is, the more helpful a second or third point would be. It's up to you. So if we try, where's my one? Okay, so we're going to stop there for today because we are out of time and we don't want to start the application. So this is the assignment.